Okay, let's wire this all up.
Okay.
Okay, so jumper wires, yeah, that goes to ground, good. And that goes to ground. And that goes to R2, good. And then those connect. Yep, pretty simple. Connect, connect, good. And there, that goes to C. And then that goes to the base. So it goes to the right. Yeah, that's good right there. And then you need to connect the emitter to R3.
Okay.
Okay, that's all looking pretty good. So what we're going to be doing is, oh, let's change our cap to be 10 micro. And just a quick review of all the other components. They look good. So what we're going to be doing mostly is in step number 5, it says, find and record the values of VBE, VB, VE, VC, IC, and IB. So that's actually rather easy. If we run the transient analysis and then click on the little tags to the left. So yeah, let's go new simulation profile, call us L7. Okay. And then, yeah, that's good. And then we'll edit it and we'll do time domain transient. Okay. So we've got, we'll put in the parameters. We'll work with 1 kilohertz. So if we have 1 kilohertz, we want to see like 3 waveforms. 1/1 kilohertz is 1 millisecond. So let's make the runtime 3 milliseconds. And then we'll go step size. We'll make it 1U. Okay. And apply and okay. And then we have to set up our signal over there. So the offset is 0. Amplitude, let's make it point or 100 milli, or 0.1 is good. 0.1 is good. Okay, the frequency 1 kilohertz, and then AC, just make that 0.
Okay.
Okay, good. So I think we can run this now. And okay, before we go look at it, up over. Oh, good, they all popped on. Okay, so you can see your currents now. So what this says is we have. Oh, we got to connect that up. Okay. Okay. Might have to run that again just to see. Let's run it again since we're not sure if that was connected.
Okay.
Did it run?
Yeah.
Okay. So it says we wanted to have 0.5 milliamps. We got 594 microamps. A little bit high, but that's okay. This may be the transistor. I used a different transistor, or we were using a different transistor lab in the model in the lab yesterday. But anyway, we've got 0.59 milliamps in the collector. And then at our base, we got 2.8 microamps. So that all looks good. Our base voltage looks good. So for step 5, it wanted you to record VB. So your VB at your base, it looks like it's to the right of C1, 1.211 volts. VE is 0.597 volts. VC is 4.056 volts. And then IC is 0.594 milliamps. And IB is 2.842 microamps. So you have that all. You can you have all that, and you can list that in your report. So why don't you take a moment and capture this and cut and paste it in a Word document?
Okay. Okay.
While you do that, I'll see if somebody else joined, and I'll if somebody else joined who wants to record. Come on, why can't I come down here? I don't know why I can't grab that. Okay. Okay, Josh, are you good?
Yeah, I'm good.
Okay. I'll turn up the volume here. Um, Okay, so that's basically step 5. Let me just read a little bit more, see what else it said. In the simulation results for IC significantly different than calculated. It actually is a bit more. What I expected it to be closer to like 0.5 milliamps, but that's okay. Let's record the value of beta used in the PSpice transistor. So while we're at it, let's click on the transistor so it turns pink. Okay, now right click. And then it says PSpice model up in the up higher, edit PSpice model. Click on down a little bit, down right there, yeah. Okay, now something probably comes up, open that up a bit. And multiple parts found corresponding to model. Can you, oh, let's just go okay with that first one and see what comes up. Okay, so let's maximize that. So there's a table up above that says that your beta forward, I'm not seeing it, but let's go down in the script below where it says BF. Right now it says 220. Let's change that to 150 and then press the save button and rerun it again. Okay, so that's your beta forward. I think that's the one. Let me just look real quick and see if there's anything else on there. Yeah, I think we're good. There's a little save icon up in the upper, yeah. Okay, now let's go back and just rerun it and see if those values change. Okay, so the current came down slightly. So actually, why don't you take a moment and erase that one you did before and capture this one?
Okay. All right, I got it.
Okay, good. So now, that's all good. So that's basically step 5. So now step 6, it says, edit this PSpice model for the transistor to increase the beta by 50%. So now we'll go back to that edit model and increase it to 225 and save again. Okay, good. And we'll run it. Okay, so increasing the current gain, our IC went up. I didn't notice what our collector voltage was, but I'm sure that one moved as well. So the IC went up and the collector voltage went to 4 volts. And then the emitters at, well, they all probably shifted slightly. Yeah, I can see that the base current has changed too. So anyway, for step 6, why don't you capture this picture?
Okay. All right, I got it.
Okay. Now for step 7, it says return the SPICE model BF to its original value. So let's go back in there and edit that again and change it to 150 again and do a save. Okay, so now we're going to run the simulation 20 degrees higher. So what we do there, we can do there. This is the way I know how to do it. I think there's multiple ways to do this. But let's go into the simulation profile. Edit simulation profile. And then it says temperature sweep in those boxes. Yeah, click on that. So what you can do here, you can put in like a list of temperatures and it'll run different temperatures when you do it. We're going to run it 40 degrees higher. But what I'm actually going to ask you to do is put in 60 degrees because I'm going to assume that we're running at room temperature now, which I'll say is 20 degrees. So let's make that 60. Okay, and press apply. And then okay. And then, okay, now let's just, before we do that, let's just make some notes. Mental notes. We got 595 microamps going through the collector, and the collector is at 4.04 volts. Okay, so let's run and see how that changes. Okay, so the voltage at the collector went down, and then the current at the through the collector actually went up. And it looks like we were at like, I think 2 microamps before if I'm not mistaken, or somewhere around that. So it looks like the base current actually went up. So this circuit was affected by the temperature, nothing really dramatic. But anyway, why don't you capture that for step 6? And then when you write your report, you can just summarize all those, like make a little box or table with IC, IB, and all that kind of stuff, VC, and just pull them off of the diagram. Okay, so we've been doing this the whole time. Let's put it back at like 20 degrees C and run it one more time. And yeah, let's just, we can make that 20.
Okay.
Just to make sure we know. Okay, let's go apply and then okay. So now our current's back down to like 570. That's all good. Let's actually look at our transient response. Is that down there? Okay. Our signal source is V3 apparently. So let's go back to that. I think you had your transient response there. It was a white screen, right?
Oh yeah, that's my graph. Yeah.
Yeah. So let's go trace, add trace. Let's get rid of the currents for now. And power. We're just going to look at the voltages. So we'll look at VQ1. No, up higher. Go up higher. VQ1C. And then you can do E as well. Do E as well. And then let's do V3 plus. V3, that one, yes. So let's see what that looks like. Okay, so that's good. So what we see, yeah, that's helpful.
Hold on, I need to turn off my alarm. It's so loud.
Oh, I don't hear it. Anyway, so at the bottom we've got the signal, and that we'll add a cursor here. That bottom is our input, the blue, and so that's oscillating. That's like 0.2 volts peak to peak. And so let's add a cursor. So we'll go up to trace.
Okay, I'm back.
Oh, yeah, it's okay. Yeah, let's go add a cursor. So let's go to trace and then cursor display. Okay, and let's put it at like the peak of that. Okay, so when we're at the peak, what we see is the bottom's at the negative, and the bottom is our input signal, and it's essentially minus 100 millivolts. So we've got 0.2 volts peak to peak coming in. And so now, right now, let me move this here on my screen. We have at the peak 5.2 volts. So I'm actually going to make a note of that. And then at the valley, what do we have? Move the cursor so it's at the valley of the green.
Oh, okay. Right.
So we're at 5.2 for the peak. And then move the cursor to like the right to where it's in the valley of the sinusoid. Yeah, keep going, right about there. And then we have a minimum of 3.3. So let's see. 3.3 plus 1 would be 4.3 plus 2. So we have like 1.9 volts peak to peak for the green. And we have 200 millivolts peak to point. Yeah, 200 millivolts peak to peak for the input. So our gain is going to be 1.9 divided by 0.2, which is equal to 9. Okay, so that's not quite as good as we may have desired, because we put in a 10K for RC and a 1K for RE. So that ratio is a gain of 10. So we got a gain of 9. So it's not quite as good, but it is what it is. I mean, that's kind of the nature of these things. You often have to design and then tweak your values to get the actual gain that you want. And in fact, we'll find that when we do the design exercise. Hold on a second. I think there's somebody else who joined. Okay. So those of you who joined late, I believe there's a video from past semesters on the Moodle page where you can come and review. And also there's the pre-lab notes on the Moodle as well. Okay, so this, why don't you capture this for your lab report?
Okay.
This wasn't even actually part of the lab. I just had you do it because I think it's good to see that it's an inverting amplifier. When the base goes high, the collector goes low. And you'll basically see that the output is oscillating around the collector voltage, which is about like 4.4 or 4.2 volts. So the midpoint on that is basically the collector voltage where that one oscillates. And then at the pink one at the bottom, the emitter is oscillating around 0.5 volts, which is the bias voltage for the emitter. Okay, so were you able to capture that?
Yeah, I got it.
Okay, so finally for step 8, what it asks you to do is a DC sweep. Set up a DC sweep with VBB from 0 to 5 volts. From the simulation results, obtain a plot of VC, VB, and VE. So let's go back to our schematic. And I'm wondering if my signal will be a problem for the DC sweep. Let's get rid of that signal source for now. Let's get rid of that. And get rid of the cap and all that. That's just extraneous stuff. That was extra stuff I had you do just to show you the amplifier's performance.
Okay.
Let's get rid of those extra wires too, because sometimes they have problems with extra dangling wires. Okay, so we're good. So now we'll just set up a DC sweep in our simulation. So go to PSpice, edit simulation profile. Yeah, go there, DC sweep, and we're going to go from 0 to 5. And let's go in 0.1 increments. And I think we're good. I think we can apply and go with that. Oh yeah, good. Good catch. Okay, so now let's first look at what's going on at the collector, base, and emitter voltage. So trace, so it was VQ1B. Yeah, that's each one of those. Let's go with the base, emitter, and collector. Yeah, that and that. Let's see what that looks like. Okay.
Okay.
Okay, good. So the blue one is that your which is the blue? Is that your base?
That's the emitter.
Oh, that's the emitter. Okay, and then the green is the base. Okay, so what we see with the green is it's turning on, but it has to get to a certain threshold. See, the red one is up at the top where it's at 10 volts. That's telling you that the transistor is basically open circuit. So there's no conduction going through it. It's basically open, and so the collector is being pulled up to 5 volts. So what we see is that we've got some current coming in, but we got to get to a certain threshold before that thing turns on. So it's in cutoff. Then it goes into the forward active region, and then it flattens out and goes to saturation. So it says in the, you can cut and paste this for your report and label it, VC and VB and VE. And it says draw a vertical line. So when you put in your report, maybe you want to first put it in like a word, probably a PowerPoint or something, put some vertical lines, and then just label cutoff, forward active, and saturation regions.
Okay.
So were you able to cut and paste that?
Yeah, I got it.
Okay. And then it says on your plot, there is a region where IC is roughly equal to 0. Through the base emitter junction is slightly forward biased. So that's basically the cutoff that we see there. We see that the base has, the green one has some voltage across it, which would imply current, but it doesn't turn on until we get to a certain threshold. So that's in cutoff. So that's just a detail. And then finally here it says, for 2 values of VBB well within the forward active region, use the cursor to find the corresponding delta VC to delta VB. So here, the bottom is our, let me get this straight. Yeah, the bottom is our VBB. Yeah, okay. So the bottom is our VBB. So let's put the cursor. Do you have it? Okay, good. So let's put it, that's a good spot. So let's just record. Right there we have VB equals to 0.7. VB, I'll just call it VB1 is equal to 0.775 volts. And then VC is equal to 8.09 volts. Okay, so now let's move it forward. So let's put it, yeah, go, I don't know. Go to where were you before? Like 0.6 or something?
0.8.
Oh, okay, yeah, you were at 0.772. Okay. I think that's, oh no, let me make sure I'm not confused here. Actually, let's just make this simple. Let's put it at, let's start over and let's put it first at, no, we're good. We're good. We'll keep it there. We'll keep that number and let's just put the other one at 1 volt. Okay, so now we have VB equals to 0.94 and VC equals to 6.5. Okay, so our gain, let's see if I have a calculator here handy. Okay, so our delta for the collector is going to be, it's going to be 8.09 minus 6.5. So we have a delta of 1.59 for the collector. And then for the base, we have a delta of 0.954 minus 0.775, which is equal to 0.182. And by the way, that at the for the collector, it's actually a minus 1.59. So if I take the ratio of that, I have 1.59 volts, negative 1.59 volts divided by 0.182 gives me 8.7. So it says my gain is minus 8.7. So that's close to the 9 that we saw when we did the transient. But that basically shows you the gain. So I don't know if you wrote those down. I mean, you can take 2 screenshots if you want, or just measure them off the screen or the plot.
Yeah, I'll just do that.
Okay. Okay, so now while we're at it, let's just see what's going on with the collector current and the base current. It doesn't ask you to do that, but let's just take a look and see if it's interesting. So why don't you go to display and clear. Yeah, and we'll turn on the currents. And then we'll go to IQ, do the same, B, C, and E. Yeah, let's see what's going on there. Okay.
Oops.
So is the blue the emitter?
Yeah.
Okay, and the red's the collector, and then the other one is the base.
Mm-hmm.
So, and those are in milliamps, so they're very, very low currents over that DC sweep. Okay, so that's interesting. So, you know, the emitter is basically, you know, I think it's a point of reference. So when the collector current is flowing downward, I think the current is still flowing downward out of the emitter, but because it's going out of the emitter, it's basically the inverse. Does that kind of make sense?
Yeah.
Yeah, because the collector current is flowing into the transistor, the emitter current is flowing out. So that's why we see the negative there. But then what we also see is, the um, the base current is in microamps, and so there's just very little current is controlling that thing. And then when it goes to saturation, it increases. But I think if we were to explode that, let's right click on the left for a moment, and let's go from let's explode that a bit. So let's, instead of going from 1.2, let's go from minus 0.4, or let's go from 0. Yeah, go make that 0, and let's take that up to just 0. Let's take it to 0.2. Okay, let's see what that looks like. Okay, so yeah, just again, it's just microamps is controlling that and switching that transition. Interesting. And then you can see where we don't see the saturation on the red curve, but you can see where the knee of the curve, when the transistor is fully turned on, and then you're putting a lot of current in there, but you're really not changing the voltage. It's pretty much, the collector is basically going to be pulled down to the emitter. Anyway, that was just for my amusement. You don't necessarily have to put that in your lab report unless you want to.
Okay.
Okay, so that's good. That was pretty easy to get through. Next week we build. That's all the simulation we really need to do per the instructions. Are there any questions?
Professor?
Yes.
Well, the last couple of weeks have been pretty rough with midterms. I haven't had a chance to turn in Lab 5. Are we still able to do that?
I'm not sure. I'd have to check Moodle. I haven't graded yet. I'm out of town. I probably won't grade. I may not grade until a weekend from now. So
Okay.
as long as it's in one of my inbox, the way it works is if I sit down to grade, I grade them all, and I got to kind of get in the zone, right? And think of, okay, what I'm looking at here, what I'm looking at here. And so if it's in my inbox, in my email, either the CSUS or the SBC Global, I won't take points off if it's there when I grade. When I take points off, it's like, if I grade them all and I say, please send me your thing, and then I got to go back a week later or so and rethink the whole thing, that's where I take 15% off.
Okay, yeah, sounds good. I'll get it in by this weekend.
Okay, good.
Me too. Me too.
Okay, any questions? Okay, sorry for the late start, but yeah, I got caught in traffic. So anyway, next week we'll build, and then this is actually a prelude to our last lab. Our last lab is going to be a design project, but it's basically going to be a common emitter amplifier. So it's going to be an extension of what we've done here. So anyway, we'll get some good experience and we'll be all prepped up to do that last lab. And I think we have 4 more. So let's see, today is the 3rd. We'll build on the 10th. Then we'll do a sim. Okay, so we have Thanksgiving. So for this one, we'll finish up probably the 1st of December. And it should go pretty easy. Again, we're going to have some familiarity with the common emitter when we build the final design. Okay, thank you, everybody. I'm ready to shut this down. Are you guys good?
Yeah, thanks, Professor.
Okay, thank you. Have a good evening.
Have a good day.
Yeah, thanks, Joshua, too.